All right. Good afternoon. Happy Friday. Have made it through another week. It is now Friday afternoon, which means it is time for the deep dive. I need to shuffle around a few more windows, as you could probably tell by me staring off over here. What is up, y'all know, over in the Discord. Nice to see you, my friend, as well as on the YouTube, Maro Castellan. What is up, my friend? Sorry if I mispronounced your name. I hope that both of you are having a nice day. All right. Yes, welcome to the deep dive. If you are new and don't know, first of all, thanks for tuning in. This is a weekly live stream. My name is Tim. I go by Foamy Guy on GitHub and Discord on this stream. Typically, we work on CircuitPython. This stream was started a few years back by Scott Shawcroft, lead developer of CircuitPython. He is working a reduced schedule right now because he has recently become parent of a second child. So he's still in the sort of taking care of a newborn stage of that process. So he's working a reduced schedule right now. He's not streaming. While he's out, I am here. And on this stream, we work on stuff related to CircuitPython. If you don't know what that is, you can learn more at the main website for it, circuitpython.org. It is basically a version of Python that runs on tiny computers called microcontrollers. When you use CircuitPython with these devices, which is just one of the ways that you can program them, typically the way it works, you plug it into your computer, it shows up like a thumb drive. You just plug it in with the standard USB cable. It shows up like a thumb drive. You can edit a Python code file on that thumb drive using whatever editing software you want. When you save it, the microcontroller interprets that Python code and executes it for you. And then your code itself can interface with all sorts of other electronic doodads. That's kind of the main purpose of microcontrollers typically is connecting to electronics and making them do things, whether it's lights or speakers or sensors or any number of other little electronic widgets. Today we're going to be writing a driver for the SPA06-003 device, which allows me to transition nicely and tell you about Adafruit. Adafruit is a hardware and software company based out of New York. They're the ones who make CircuitPython possible by paying a team of folks to work on the project, including Scott and myself. If you would like to help support them in CircuitPython, as well as all of the open source software that they pay myself and the rest of the team to write and publish, one of the easiest ways to do that is by purchasing hardware from them at adafruit.com. The SPA06-003 breakout device that I'm writing the driver for is an Adafruit breakout device. The microcontroller that I happen to be using to write the driver on is a Feather RP2350, which is also an Adafruit device. So you can get yourself both of those over at adafruit.com, as well as loads and loads of other fun and interesting toys to build projects with. Doing much better this Friday than last. COVID really wiped me out last week or so. Hope you're doing well this afternoon also. Nice. Yeah, glad to hear that you are feeling a bit more recovered. That's good to hear. Yeah, it's only rough. Be knocked down with any kind of sickness, but definitely COVID's no fun. All right. So I do have this Feather plugged in to the breakout, and I actually am just starting this. So I've been working on a different guide for the majority of the day today. So I am kind of changing gears here into CircuitPython and driver, I2C driver land. So I just sworn I had some smaller stemma cables than this, but I don't know where they're at. I gotta go find them. Perhaps I am out of ones that have not been used in projects. These things are really convenient, so I tend to just use them anytime that I can inside projects. So lots of them are just sort of stuck in stuff that I have made over. Anyway, it doesn't really matter. You can see there, SPA06-003. There's the breakout. It is connected with the stemma cable. It's a bit too long for me to really get both in the same shot very well, but we've got that plugged into a Feather RP2350. And it is here. I've got the camera on it, but truth be told, it's just going to be kind of sitting there anyway, not doing a lot of anything. The real action is going to be over here on the screen, which should that drive like I was talking about before. One thing to check for, I have no idea what I would have done on this Feather most recently. It's possible. Oops. It's possible. Ah, okay. So I think potentially that. Yeah, so this Feather, I think, is running an Arduino program right now. So I just unplugged it. I'm going to verify that that disappeared. Yeah, okay. This Feather has got an Arduino something or other on it. I'm just going to load CircuitPython, hold down the boot button, press the reset button. Here, Feather RP 350, beta 3. What do we got? Tack. Need some blue tack or something. Oh, there you go. That'd be good. I actually do have some stuff around. I like that. Actually, interestingly enough, that's actually probably where one of my small stemma cables is in a box connected to a sensor, which is held down with that stuff. Yeah, I love that stuff as well. Sticky tack or blue tack. I've got some that's gray, but it's, I think, the same thing, just like some sort of gummy, sort of clay-ish type stuff. You squeeze it up. For anyone that doesn't know, you kind of just squeeze it up, warm it up in your hand, and then it gets a bit sticky. You can use it to stick stuff sort of temporarily, which would be quite useful. The other thing that is quite useful, albeit a little bit more fiddly potentially, is these, which I keep meaning to pick up some of these as well, but I still haven't done it. But these swirly aluminum plates are really nice with the breakouts and the feathers because they're all sized and spaced so that these sort of corner mounts that are pretty standard on Adafruit breakouts and microcontrollers can fit in there. That would be a nice thing as well, because then everything's all nice and clean, and it holds all the wires instead of just letting them all crazy. All right, looks like this is wiped fresh. Good place to start from. SPA00, well, it's 06. I think we'll just leave it at that. There are others beyond the 003. We'll maybe include that in the class name. I don't know that it needs to be in the file. Of course, we still have time to change it. Here though, and I will also specify that this is an I2C driver. Put a address there for us. So I'm basically gonna reference the one that we worked on last couple of weeks. I was doing some SPI work the last few weeks, but before that, I wrote the I2C driver for the BMP5X. And we're back in I2C land. We're getting the I2C driver going first. I am still working on SPI a bit, but I I guess you could call a speed bump or a hurdle. Essentially, I need to get a hold of a logic analyzer to troubleshoot that. So what I have realized on the SPI front is that I kind of was getting it working. So I had made a first version of it, and then I was working on another iteration, which refactored it based on conversation I had with Scott about it. And I got the new iteration sort of hammered out, and it was not working consistently. I could kind of get it working sometimes, sort of, but not really that much. Go to the Arduino driver for this. Adafruit SPA06. See if that gets me there. If not, then I'll just go to direct. That looks like it. So I had a new iteration. I worked on this the last couple of streams. So if you're interested in that, you can go back to those and watch it. It was I could kind of get it to work sometimes, sort of, but not consistently. And in troubleshooting that to try and get it to work consistently, I was going back to some of the prior versions of the SPI driver that were working. And I was realizing that even though they appeared to be working, they were not actually working all the way. They were indeed getting temperature and pressure sensor data, but it turns out I think the writes, either the writes were not working or the reading of writable registers was not working. One or the other. But what I was noticing troubleshooting this is that even in the SPI driver that was working, that appears to work correctly, when you write like a configuration value, for instance, the oversampling rate or one of those things, there's a load of configuration values you can write. A bunch of them get written in the init function. When you write those things, if you then just immediately read them back, they don't contain the data that was written into them. So there's something going wrong with writing. And I don't have any better ideas for troubleshooting that than really straight up just getting a logic analyzer to look at the signal on the wire and see what is happening. Okay. Gonna look here just real fast at what is in the Arduino driver. This one, it does look like is a little bit simpler than the BMP. The BMP one that we worked on before, it was kind of a wrapper around the Bosch provided code. This one appears to be just directly sort of doing register stuff in the Arduino code. It's not a wrapper around some other thing. That is nice, and it does not appear that there's really all that much stuff going on here. It's looking like a pretty reasonably sized driver. There's not too much stuff here. One thing I don't, I was about to say, one thing I don't see is the address, but in fact it is right there. Actually, I'm just going to get the value. Okay, and much like the BMP5X, it has the ability to have an alternate address, which I believe is going to be 76. So I'm going to want to double check that at some point. Default frequency. Should we keep this whole name? I guess maybe we should just keep this whole name. Plates are cool. I picked up a few sizes. Definitely good for prepped in advance setup. Some tacky mounting putty would be good for on the go. Yeah, that'd be the nice thing, is I could keep the putty just here on my desk and really, really quickly stick something down without needing a screwdriver or anything like that. All right. I wonder if you could just pre-mount pegs in those things instead of using screws to actually affix them to those aluminum plates. I wonder if you could just get a bunch of little pegs in there and just kind of like set your stuff on those pegs. Might be interesting. I'm gonna get a couple more of these things while we're here. Means, I guess these are kind of just arrows essentially. Go ahead and grab all of these. In fact, I'm just gonna grab all of these and have our friend friendly cloud E code convert these for us. I don't know if Cloud's middle name is E. I just made that up for the record. I don't even know if Cloud has a middle name. Can you please convert these code to copied that first, so let's give it that. We have a couple, so I can just give it probably enough for it to rest of these for us. This is like the perfect kind of thing, like get some crazy code out of these things sometimes for sure. But this kind of thing where it's like take this structured text and convert it into this slightly different structure. Be good at that kind of stuff. And it took the little arrows out, so I guess I'm going to get rid of that one as well. There are a couple enums here for sample rates. We'll deal with those in a little while when we get to it. Let's just get this started. Chip ID is always a kind of like the first thing to do anyway here, so no reason why not. They got standoffs. They likely have standoffs so you can mount with screws to the plate, but it have clips on the other end. Oh, clips would be interesting too. Store used to have board edge clips as well to use with their acrylic board and half mounting base. You have a poke around. Oh, I changed the name of this. Address there. All right, and the way these drivers work is we're going to be using register. Let me install that. Root register onto the device. That's going to give us access to the bits and RO and RW type stuff. Adafruit register bits. I'm just going to import all of them. Okay, register ID is there. The other thing we should open up is the data sheet. We'll hopefully have like a register map. Not color coded like the BMP, which was a nice touch, but it'll do. Here, ID address is 0D, which matches what we had in the code, so that's good. I did not just hallucinate a new register address, at least for that one. I should download this as well. Is there no I'm actually going to open that a little bit easier to tab back and forth. It's not in the browser. Also, on as a added bonus, we do get the dark mode. Certainly. Guys, 0D. So it's got a revision ID and a product ID. So let's just read both of those, I guess. And those are what? Those are 4 bits each. What is this? Reset state. Okay, 11 hex. Oh, okay. So that's gonna, yeah, that's gonna be the whatever bits map to hexadecimal value 11. I do not know, but that's fine. So revision ID, I'm assuming that's product ID. Maybe let's take a look. I wish I could open 2 copy, or like really what I want is 2 tabs inside the same copy of the PDF program. I think this program does that. Product and revision ID. Oh, these doesn't. Just product and revision. I was gonna see if it said anything more specific about like what that means really. Those are read only, I'm sure. Doesn't. Does actually read there. Bits needs to be a number of bits, and then you know what, I actually want these in Python for right now. So I'm still not quite 100% memorized on the API. I know we need the number of bits, we need the address, we need starting bit, but I don't know which order they're in and if there's anything. I know there's a couple other optional ones. I don't know if we'll need them. Last I knew these were out of stock, but the clips. Let's take a look at that. Oh, right. The link thing. Wait, how did I do this before? It was oh, I highlighted it. That's right. Highlighted it. Remember that. Oh, okay, yeah. I know these. I've seen these before. That's an interesting idea, actually. I do kind of like that idea. Wonder actually if these fit. Be kind of cool. W bits. It does take the number of bits, the register address, the lowest bit. Those are the most important ones typically. So we have 4 bits. We have an address that is the ID, register ID. We have, for the product ID, the lowest bit is 0. And for the revision ID, it is also 4 bits. It's the same register, but the lowest bit is going to be 4. Let's look in the Arduino driver and see if it does anything before. Checking the chip ID. A lot of begin. Oh, because they're different. So that's SPY. Oh, interesting. Okay, so there's one begin for I2C. There's one begin for SPY that is a SPY object. And then there's one begin for SPY where you would give it individual pins. So I guess that's like on a board with a built-in like board.spy is what we would call it in CircuitPython. In Arduino, obviously it's a bit different, like SPY address reference there, but Mostly interested in I2C, and all it really does in the I2C one is set SPI to null, initialize the I2C device, call underscore init. Assuming is after the other SPI constructor begins. Yeah, okay. No, okay. So it does not do anything before getting the chip ID. And it is address bit 8 high to read. Yeah. That's the very first thing it does. This is actually similar to the CircuitPython API in a way, because it's creating the register object and then calling read on it. Or what this part is. Here anywhere else? Or one thing we could do is clone this and open it in the local IDE. But well, they're checking it for 0x11. So they must be, in fact, reading the whole thing, I guess. They read. This almost sounds like the SPI thing. Like how on SPI, it's using the high bit as either 1 or 0 to signify either reading or writing. But you would not need to do that for I2C, so I guess inside of here, maybe it handles it separately for SPI and I2C. And then I guess that's going to be telling it to read an entire byte. So maybe we should actually just make one thing called chip ID and have it be 8 bits. Because we're going to want to check it against 0x11 anyway, which is what this is doing. So we're going to need it as one value. Okay. Let's really just print the chip ID. Which we're going to be able to see unless we here. Okay, yeah, we do need to save on the object. Well, we need to create the I2C device. It's inside of a NIT. Okay, there we go. So we got 17, but that's decimal. Go. So we can basically do the same thing Arduino, basically. Just check for 11 if it's not that. We do, what kind of errors do we do in BMP? Value error. Value error on all of them. Well, consistency I think is best, but in hindsight I don't necessarily value error. I mean, I guess the thing is not the value we're expecting. That's a value error, I suppose, but bet JP could 3D print something if DigiKey doesn't already carry what I need. Yeah. Okay. That'll check the chip ID. So far, so good. And went crazy trying to read that, so we're fine. Does a soft reset next, and then delay 10, I think. Is that 10 milliseconds for Arduino? It's milliseconds, I think, maybe. So we need to find reset. That one. Okay. So that one is going to be only doing 4 bits, unlike the last one we saw, which was just reading a full byte. It is still broken out. I think this might be the first Arduino... The first one? Maybe not the first one. But unlike the last one, it's nice because this is like... it's the same conceptually as what's going on in CircuitPython. We don't have to do it in 2 steps necessarily. Like, this is kind of like reading a full byte, and then this, it looks like, is kind of like setting up to get the 4 bits we care about. So that part of it is a bit different. It's also getting created right here and then used and then presumably thrown away after reset function is over. Whereas ours get created in the body as descriptors, and then you could just use them whenever you want. And they don't have to get created every time. But conceptually, it's pretty similar. It's like setting the register address. It's setting, in this case, also the SPI information about it, how much to read, and then how many bits. And I presume that that is the lowest bit grab. So I'm guessing that we're looking for the early 4 bits, the lower 4 bits of the reset register, which should have gotten pulled over, I think. There we go, right there, 0C. Let's double check that is correct. Can you bookmark parts of a PDF? Be cool too to bookmark the register map. Page 21. I see nothing for bookmark. That was 0C reset, and indeed the lower 4 bits are soft reset. And unlike another thing that the BMP datasheet did really nicely is these were clickable. I could click this and it would go to it. One doesn't do that, but that's okay. So we know it should be after value, the reset register. We could search 0xC. We could search. I think they don't list the address again down here. Okay, so Yeah, it is the lower 4 bits, 0 through 3. Write in binary 1001. That's a fascinating way to do that. Soft reset will run through the same sequence as a power on. All right. So, and it looked like the Arduino code, it just wrote constant of 9, which I assume is the same. Bin of 9. Yeah. Go ahead and make things here for that. Let's call it command set. Let's call this the... So is there a separate command register, or is this kind of like just the command register? No, okay, this is the soft reset and FIFO flush. All right. I guess we'll call this soft reset. They are writable. You want 4 bits, reset, lowest bit 0, right? If we validate the chip ID, the next thing we want to do is set the soft reset command. Maybe we should make it a function? Should we have it be a function? Reset function? Did I do that in BMP? Well, BMP is a little different because I did do that here. So it has a command register which can take different commands that some of them are not related to resetting, whereas this one doesn't. But truthfully, the same kind of here. I think what we do is go like that, reset, and then define a reset. And in there, what we're going to do is set this to the reset command. And just like the Arduino driver, well, so it's doing it outside of here. I almost think we should just sleep inside of here. So it said 10 milliseconds. Yeah. Right? Because that's 100 milliseconds. 10 milliseconds. Self. Okay. That just writes and then returns its value. Where this is called from. That didn't work actually. Wait for coefficients and sensor to be ready. Is coefficient ready? Is sensor ready? Coefficient ready. So that looks like it's going to be a single bit. These are coming from the same register. Measure config register. Let's easily see the... Have that. Well, it should be the same name in ours, actually. Work when I copy. 08. Double check it. Since I did have... I'll translate all of those. It's good to just give them a once over. Like sensor ready, temperature ready, pressure ready, coefficient ready. Yeah, okay. Coefficients will be read to the registers after startup. Not available are available. It looks like there's basically one of these for each kind of thing it can do. And then there's a sort of mode thing at the lower bits of this, which we're not to yet. So we want to start with sensor ready and coefficient ready, which were the first two that the Arduino driver checked. Coefficient ready, sensor ready, these were the first two that it checked. And it's actually looping as well, so it's while those things are not true, sleep for 10 milliseconds. I have ready. I think that's an RO bit. Yeah. We don't have a number of bits because it's a single bit. We do have a register, which was the measure config register, lowest bit, or the index for the coefficient ready was 7. It was actually the highest bit. Sensor ready is the next one down, bit with index 6. So we reset, and then while not sensor ready or not efficient ready, sleep. I wonder if we want a timeout here, maybe. I mean, theoretically, we already got past here, so we know like we're connected to a thing that has the right I2C address at least. The Arduino driver doesn't seem to have a timeout, but might be good so this doesn't, because right now this would just stall forever if those never became true. For now, say sensor and coef. If we make it to there. Nice, okay, very good. Okay, so read the calibration coefficients. Calibration coefficients from the registers. True if successful, false otherwise. What is it going to do with it? Because it's returning true or false based on if it was successful, but it's like read coefficients. Like we must be doing something with them. So read all of it. 21 bytes. Okay. Back to page 21 for the. It says 10. Up to. Listed here. Rex 10 to 24. Oh, bottom obviously. See register description. Calibration coefficients register contains 2's complement of coefficients that are used to calculate and calculate the compensated pressure and temperature values. Okay. There are a lot of these. Well, yeah. Kind of a lot of these. So look at the Arduino code again. So that is going to set up a register to read 21 bytes, starting here. Really, I mean, I guess in here is where they're going to end up. They are not put there yet. Okay, here we go. Here we go. So read. That's presumably read data from this register into this buffer. Read that many datas, 21 bytes. Parse the coefficients according to the data sheet. Okay. So, hmm. Okay, I think what we will do for these. So this is reading 21 bytes and then parsing all the values out of those 21 bytes, which is effectively what the datasheet describes as well. But realistically, what it has is C0, which is a 12-bit number, C1, which is a 12-bit number, C00, which is a 20-bit number, 10, 20 bits, 01, 16 bits, 11, 16 bits, 16 bits, 16 bits, 12 bits, 12 bits. So I think in our case, we just make RW bits instances for each of these. And I think there's even a 2's complement thing on there, isn't there? Signed? Yeah. I think that we can use to do some of that for us. We just set that to true, and then I think that stuff is just going to work correctly. Does this tell us default values? Or I guess they don't have default values because the whole point is they're like a calibration. Okay. So probably what I'll need to do is run the Arduino code and print these out and then make sure that they're correct. Okay, now with RW bits, it will be a bit tricky because we have the, like C0, for instance, it's 12 bits, so we know it can't be contained in a single byte. It's split across 2 bytes. So our register width is going to have to be 2. And we're going to have to use the lowest bit index to essentially target only the bits we care about in those 2 bytes. One question is, do we just create C0, C1, C11, all those things? Or maybe I'm thinking we call them coefficient 0? C0 is kind of really tell you a whole lot. Maybe one of those, perhaps. And these are read-only, or? I mean, we're certainly reading them. Not actually specify. I assume that that's a read-only kind of situation. Okay, so number of bits, 12. The register is 10. Do we have that? Yes, actually. But we're going to want more of these, I think. I'm pretty sure we're going to want more of these. but we'll start with that one for now. That's the address. We have... Okay, so we're going to have register width is 2, which is going to make our index, or our lowest bit, so we would be at 0, so to be bit 4, I think is the way that would work. And then register width 2. That would read code. Five. Since it doesn't say in there what to expect, really, just have to assume that's correct. Unless we would go run the Arduino, like I said. So coefficient C1. Also, two registers, but it's going to be lowest bit 0, and then I think that should work its way back that one, but this would be our address. I'm almost thinking here you go like register coefficient C0 1, this sort of number here. $22. Right? We don't. Easy way to. It's correct. C00 looks like it's 16 bits. That first two of them were 12. 12, 12. Oh, it's 20. So then C00 be 13. Now 20 bits, 3 registers, 3 of these, 13, 14, and 15, and we want to be lowest bit 4. Also, I forgot to turn on sign. Defaults to false, which means probably those numbers we printed are wrong. We had one of them stayed the same, the other one changed. Although I did wreck this one by clobbering this thing. It's what got printed last time. Okay, it did change, but it changed to something else. And then obviously the 0, 0 is now that one. C1 stayed the same. Okay. All right, so we had C1, we had C00, 20 bits. We have now C10, 20 bits. Did these not have better names? Is there not have a purpose for each descriptive? 0, 1, 0, 1 without 0, like very confusingly named in my opinion. All right, 20 bits. One of these. That is C10. That is also 3 width. It's gonna start on. So this is actually. So is it's gonna start on 15, I guess. But it almost feels like we would want to start it on 7, but we don't because we're reading afterward, right? So we start here, read 3 bytes. Lowest bit we're interested in is the 0 index bit, all the way at the very end. Zero, so yeah, 15 and then 0. 15. Lowest bit is 0. I have register with 4. 3. Also, was the lowest bit actually 0? On the last one, it wasn't. The lowest bit on the last one was 4. Got that. Yeah. C00, lowest bit is 4. T1, lowest bit is 0. C0, lowest bit. So 4, 0, 4, 0. And then C1, 0, lowest bit is 0 again. Okay, so again, that one that was bigger negative. Yeah, it's changed again. Okay. Got some more values there. We are basically at time as well. Stream is usually an hour these days. How many more of these are there? So there's like 1, 0, 0, 1, 1, 1. So 0, 1, 1, 1, 2, 0, 2, 1, 3, 0, 3, 1, 4, 0. 7 more. More. A lot of random values in there. Well, they're not random, I guess, but okay. That is basically going to do it for deep dive for tonight, though. If anyone's got any last minute questions or comments, get those in. I will be back tomorrow over on my own stream. I will probably just continue working on this. So if you would like to see some more level I2C driver development, come and join me tomorrow morning, 10 a.m. Central Time. I usually drop the chats in the Adafruit live broadcast chat when I get started. So if you want links, that's where they are. Yano says, if I can ask, when you are approaching working with / from registers, what do you personally look for in the documentation to help you get oriented in terms of understanding how a specific register is set up? Word length, endianism, word size, etc. Take this documentation, for instance. So I will freely admit, like, I'm still really new to writing this kind of driver. This is probably like 3rd or 4th one that involved like actually looking at a data sheet and getting relevant information out of there. So yeah, take what I say with that in mind, is that I'm still very new to this. That being said, I'll give you the best. You're fine. You're fine. That being said, I'll give you the best answer that I can, which is that in the last 2 data sheets that I worked in, the BMP5X and then this one here, SPA06, the parts of the data sheet that I found most useful were the map, the big map that we were on page 21 in this data sheet. So this one basically lists every single register that we're allowed to access, everyone that has anything interesting to us. and even some that just have blanks that don't really matter to us. Internal use or whatever is what the BMP called those. So the map has got everything all laid out, which is where you can find, obviously, like your addresses and your stuff like that. You can also get a look at, not for this coefficient one on this data sheet, because they just put a pointer to there, but, you know, get a look at this kind of thing where it's showing you which bytes are which thing. Indianness, I'm not sure if the data sheet spells it out anywhere directly with that term or not, but I presume based on the order of the bits here, with the high bit being on the left and the low bit being on the right, that it's that little or big. I think that's little, but I'm not certain. Indian does not appear anywhere. I'm not sure if I spelled it right. I don't use the term a lot. E-N-D-I-A-N. I think that's right, though, is it? I think that's right. So it does not appear. So that is one thing the data sheets, like, sometimes don't spell out basic information that you definitely need to know using the terminology that you might expect. Like, kind of have to know, it seems like, to look for sort of the way the labels in the table are, or the way the labels down here are, which I would say, wrapping back around, the two parts of the last two data sheets that I've worked on that I've found most helpful. One of them is the map, like I was just saying. The other is the register descriptions, which were below the map on both of these. And these are like listed out each register, and then what, you know, value is in which bits, and then if there's more to know about it, it tends to tell you here. So it's like, you know, it might tell you like whether, it might tell you like what a 1 represents and what a 0 represents, for instance. Maybe the ready ones? Did the ready ones say that? Or did they just assume that 1 meant ready? Now, okay, so like this right here, yeah. So in the register descriptions, you could get more stuff like this, where it's like the map tells you where that data's at. The descriptions tell you like, what does it mean? So, okay, I read the bit out of there, and then this is more like, based on what you read, here's the actual like real world, what does that mean? Example, they sometimes have an application example that uses some of the registers you'd have questions about, or just explain in related sections about the endianness of the details or reconstructing the bits. Yeah. Example code, that's the other thing, is like, I'm really, really new to reading data sheets. I'm really, really not new to reading code. So, like, I don't write a lot of Arduino code. I'm not formally trained in C++ or anything. I don't necessarily know the language per se, but I have read a lot of code that does a lot of things in my day. So that's the other thing, is like those two areas of the datasheet, register map, register descriptions, but the code I think is king, which is convenient for me because I tend to be working on the CircuitPython driver after the Arduino driver has already been implemented. So I already have a baseline implementation, you know, in Arduino C++ that I can reference as I'm going back and forth. But yeah, I think that's the best answer that I can give. Register map, descriptions, those are my sort of two go-to areas. The other thing, you know, that I find really helpful in both data sheets has been find, searching for what you're looking for. It seems like different bits of data is all over the place, not necessarily connected to, you know, locally next to the parts that are relevant to each other. So search is really handy, but yeah, code is king, honestly, even better than the data sheet, if you have a driver that works or some demo code that works. All right, that is going to do it for the deep dive. Thank you again for everyone who watched. Thanks for the folks in the chat. Thank you to Tyeth as well over on YouTube. Nice to see you, my friend. And like I said, I'll be back tomorrow over on my stream. I'll pick up where I left off here. We'll keep working on this driver. So yeah, until then, I will bid you farewell. Thanks for watching. Hope you have a good night, and I will see you later.